Hey everyone, ready for another deep dive? Today we're going to tackle some really cool AI research.
Oh yeah, this one's a good one.
Definitely. A paper called The Surprising Effectiveness of Test-Time Training for Abstract Reasoning.
Catchy title, huh?
It is, and it's accurate too. We're talking about test-time training.
TTT for short.
Right, TTT. And it could be a game changer for how we think about AI's potential.
No kidding. Imagine AI that can actually learn and adapt while it's solving a problem,
Whoa.
instead of just relying on what it's already been trained on.
So it's like it's thinking on its feet, like we do.
Exactly. It's a huge shift from how we traditionally train AI models.
Right, usually we feed them tons of data beforehand and then test them.
Yeah, exactly. But TTT flips the script. The model keeps learning during the test itself.
So like it's constantly updating its strategy as it gets new information.
Exactly. It's like, okay, I've never seen this before, but let me see if I can figure it out.
That's pretty mind-blowing. So to really push the limits of this, the researchers chose a benchmark that's known for being really tough.
Oh yeah, the Abstraction and Reasoning Corpus.
ARC.
Yep, a whole bunch of visual puzzles that require serious reasoning skills.
Like those brain teaser games that make you stare at shapes for hours.
Uh-huh, yeah, kind of like that. But for AI.
And I'm guessing even the most advanced AI struggles with these.
You bet. ARC has been a major roadblock. That's exactly why the researchers chose it.
To see if TTT could help AI crack the code of abstract reasoning. Something that we usually think of as, well, a human thing.
Exactly, like a core part of what makes us intelligent.
So we've got this new approach to AI training.
Mm.
And this benchmark that pushes the limits of AI reasoning. How did they put it all together?
Okay, so they took a large language model, and instead of pre-training it on a huge data set of similar tasks, they focused on training it during the test itself.
Interesting. So they kind of threw it in the deep end?
Kinda. And here's the kicker. One of their big findings was that pre-training on massive amounts of synthetic data actually hurt performance on ARC.
Really? That's so counterintuitive.
I know, right? You'd think more data equals better results.
So what do you think is going on there?
Well, it makes you wonder about the quality of the synthetic data we're using to train AI.
Maybe it's not as representative of real-world problems as we thought.
Could be. Or maybe we're just focusing too much on quantity over quality.
So it's not just about feeding AI a fire hose of information.
Right. It's got to be the right kind of information, stuff that actually helps it develop the specific skills it needs for the task at hand.
Makes sense. So if pre-training wasn't the key, what were the magic ingredients for successful test-time training?
They focused on a few crucial things during the test. First, they created a specialized data set just for TTT, derived from the ARC training set.
So like instead of overwhelming it with 100 puzzles at once?
They started with a few examples, let it try, and then guide it through the process.
Okay, so it's about giving the AI these bite-sized learning experiences that build on each other.
Exactly. They used something called leave one out tasks.
Leave one out.
Basically, they remove one example from the training set and treat it like a mini test to force the model to really think clever. And did they do anything else to help the AI along?
Yeah, they also use these cool transformations, like rotating and flipping the puzzles.
Ah, so it's like showing the AI the same puzzle from different angles.
You got it.
Yeah.
To help it grasp the underlying concept, not just memorize a solution.
I like that. It's like seeing the forest for the trees, understanding the bigger picture instead of getting bogged down in the details.
Precisely. And get this, instead of using one adapter for all the tasks, they trained a separate one for each individual problem.
So each problem gets its own custom-tailored learning experience.
Yep. It's a level of personalization we don't usually see in AI training.
So this adapter thing is like a specialized tool that helps the AI solve that particular puzzle.
Exactly. It's like a mini neural network that gets added on top of the core language model.
Okay, so it's giving the model a specific skill set for that task.
And it uses something called low-rank adaptation, LORAO, to do it efficiently.
All right.
Yeah, it's a way to adapt the model quickly without having to retrain the whole massive network. Gotcha. So it's like streamlining the learning process. Okay, so we've got our model equipped with these adapters, learning as it goes. But when it actually tries to solve a puzzle during the test, does it just take one shot and move on?
Not a chance. That's where augmented inference with hierarchical voting comes in.
Whoa, hold on. Break that down for me. What is augmented inference?
So instead of generating just one answer based on the input grid, the model uses those transformations, we talked about the rotations and flips, to create multiple versions of the problem.
So like it's looking at the puzzle from different perspectives, gathering different opinions before making a decision.
Exactly. And each of these transformed versions is fed through the model, and it generates a bunch of different possible solutions.
Okay, I'm following. And then what's this hierarchical voting all about?
So it's not just about picking the most common answer among all those variations.
It's got to be more nuanced than that.
Right. The model uses a system to weight the different predictions based on how confident it is in each one and how well they fit with the rules it learned during training.
So it's like having a panel of AI experts, each with their own take on the puzzle.
Aha, I like that.
And then they all vote on the best solution, taking into account their confidence in the underlying logic.
Exactly. It's way more robust than just taking a single stab at the answer.
This is amazing.
Yeah.
So after all that clever design and training, did TTT actually work? How much better did the AI perform?
Well, the results were pretty surprising.
In a good way, I hope.
Oh, yeah, definitely. TTT led to a huge improvement in accuracy, up to 6 times better than traditional fine-tuned models.
Wow.
And by combining TTT with another method called BRC, they actually achieved state-of-the-art performance on ARC.
That's incredible.
And get this, they even reached a level of performance comparable to the average human.
That's mind-blowing. So this isn't just about AI getting better at puzzles, right? What does this tell us about the bigger picture, the future of AI?
I think it points to a fundamental shift in how we think about AI training.
So instead of force-feeding models information beforehand,
maybe we need to focus on their ability to learn and adapt in real time, like humans do.
So it's not just about memorization anymore.
Right. It's about true learning and problem solving.
And if we can get these kinds of results on something as complex as ARC.
Imagine the possibilities.
All right, so we've covered a lot of ground in this first part of our deep dives.
Definitely.
We've talked about this surprising effectiveness of test-time training.
Right.
The challenges of the abstraction and reasoning corpus.
Those puzzles are tough.
And the potential of TTT to really change how we think about AI.
It's pretty groundbreaking stuff.
But before we get too lost in all the possibilities, let's take a step back and really break down how TTT actually works.
Good idea.
Let's start by delving a little deeper into ARC.
Okay.
You mentioned these visual puzzles. What do they actually look like? And what makes them so challenging, even for us humans?
All right, so imagine a grid kind of like a chessboard.
Okay, I'm picturing it.
But instead of black and white squares, you have these colorful shapes and patterns arranged in specific ways. Each puzzle gives you a few input-output pairs.
Input-output.
You see a starting grid and then a transformed version of that grid.
So like a before and after picture.
Exactly. And the challenge is to figure out what rule was applied to create that transformation.
Oh, I see. So you're trying to crack the code to figure out the logic behind how the grid changes.
Exactly. But the catch is you only get a few examples to work with.
Oh, so it's not like you have a ton of data points to go off of.
Nope. You got to deduce the rule based on limited information.
Sounds tricky.
And then use that rule to predict what a new output grid will look like based on a new input grid.
So you have to generalize what you've learned to a completely new situation.
Precisely. That's what makes these puzzles so challenging. It's a real test of abstract reasoning.
No wonder AI has traditionally struggled with this.
Yeah, it really requires a different kind of thinking than just memorizing patterns or following pre-programmed rules.
It's about understanding the deeper logic, the underlying principles that govern how things work.
Exactly. And that's why ARC has become such a popular benchmark for evaluating AI systems.
Because if an AI can solve these puzzles, it suggests it has some level of that abstract reasoning ability that we usually associate with human intelligence.
Right. It's like a proving ground for AI.
Pushing the limits of what we thought machines could do.
And what's remarkable is that test time training seems to be giving AI a real advantage in tackling these kinds of challenging reasoning tasks.
It's like it's unlocked a new level of understanding.
It really does point to the potential of this approach to fundamentally change the field of AI.
I'm excited to dive deeper into how TTT actually achieves these impressive results on ARC.
Me too. Let's unpack some of the key techniques that made this approach so successful.
Let's do it. We'll pick up right where we left off in the next part of our deep dive.
Sounds good. So we were talking about how the researchers structured the data for TTT.
Right. Using those leave one out tasks and transformations to help the AI understand those abstract concepts.
Yep. Those are definitely important. But there's another piece of the puzzle.
What's that?
Adapters.
Ah, right. You mentioned those before.
Yeah.
Like specialized plugins that give the model the skills it needs.
Exactly. Instead of using one generic adapter for all the puzzles, they trained a separate one for each problem.
Oh, wow. So it's like giving each AI its own personalized tutor.
Pretty much, it's like a tailored learning plan.
Makes sense. A one-size-fits-all approach rarely works for AI or for people.
Right. And they saw some really good results with this. Training a separate adapter for each task really boosted performance on ARC.
So it shows that customizing the learning process for each challenge makes a big difference.
It really does. Okay, so we've got our AI set up with these specialized adapters learning from each puzzle.
But what happens when it actually has to solve a puzzle during the test? Does it just give one answer and that's it?
Nope, not at all. They actually use something called augmented inference with hierarchical voting.
Okay, well, no, that's a mouthful.
I know, right? It sounds complicated, but it's pretty clever once you break it down.
All right, let's break it down. What's augmented inference?
So remember those transformations we talked about? The rotations and flips.
Yeah, they help the AI see the puzzle from different angles.
Right. Well, instead of just generating one answer, the model uses those transformations to create multiple versions of the problem.
Ah, I see. So it's like the AI is brainstorming different approaches.
Exactly. Each transform version gets fed through the model, and it comes up with a bunch of different possible solutions.
Okay, I'm with you. And then comes the voting part.
Right. But it's not just a simple majority vote.
It can't be that straightforward.
Nope. The model actually uses a system to weight the different answers based on its confidence level for each one and how well they fit with the rules it learned during training.
So it's like the AI is evaluating its own ideas.
Exactly. And it factors in both its intuition and the logic it's learned.
That's really cool. It's like a much more sophisticated way of problem solving.
It is, and it turned out to be really effective.
So all this fancy training and clever design, it actually paid off.
Oh yeah, big time. They got some incredible results on ARC.
Give me the highlights.
Well, for one, TTT led to a massive jump in accuracy, like way better than traditional training methods.
How much better are we talking?
Up to 6 times better.
Whoa, that's a huge difference.
And by combining TTT with another method called BRR, they achieved state-of-the-art performance on ARC.
State of the art. So that means they're at the top of the leaderboard.
You got it. No other AI system has done better on ARC.
That's amazing.
Yeah.
But it's more than just about puzzles, right? What does this mean for the future of AI in general?
It definitely has some big implications. It makes you rethink how we approach AI development.
Like maybe we've been doing it wrong this whole time.
Maybe. We've been so focused on pre-training these models with tons of data.
Right, like cramming for a test.
Exactly. But what if we focused more on their ability to learn and adapt on the fly, like we do as humans?
So it's not just about what you know, it's about how you learn.
Exactly. And TTT seems to be a way to unlock that kind of dynamic learning in AI.
And if they can achieve these kinds of results on something as tough as ARC,
Who knows what else they can do?
right, the possibilities are endless.
So we've talked about all the cool stuff TTT can do.
The improvements in accuracy, the state-of-the-art results.
But it's important to be realistic, too. TTT isn't perfect. There are definitely some limitations.
Okay, let's talk about those. What are the drawbacks?
One of the biggest challenges is computational cost.
Ah, so it takes a lot of processing power to run these TTT models.
It does, more than traditional methods, because the model has to constantly update its parameters during the test.
So it's not something we can easily run on our laptops just yet.
Not really. Not with current technology, anyway. But researchers are working on making TTT more efficient.
So it's a scalability issue. We need more powerful computers to handle the demands of TTT.
Exactly. Especially as we start applying it to bigger and more complex AI models.
Right, and even with more powerful hardware, there will always be some tasks that are better suited for traditional training methods.
Definitely. Like tasks that require extremely high precision, like medical diagnosis or self-driving cars.
Yeah, you don't want the AI learning on the job when lives are at stake.
Exactly. In those cases, you want the AI to have a really solid foundation of knowledge before it starts making decisions.
So it's a trade-off. TTT is powerful, but it's not a universal solution for every AI problem.
Right. It's important to choose the right tool for the job. Sometimes the tried and true methods are still the best.
Okay, so computational cost is one limitation. Any other challenges we should be aware of?
Another big one is data quality.
That makes sense. If the AI is learning from bad data, it's going to produce bad results.
Exactly. Garbage in, garbage out.
So we need to be extra careful about the data we use for TTT.
We do. It has to be accurate, unbiased, and representative of the real world.
And that's where human oversight comes in.
Absolutely. We need experts to curate the data and monitor the AI's learning process.
So make sure it's not picking up any bad habits.
Exactly. So TTT is powerful, but it's not a set it and forget it solution. We need to be actively involved in shaping its learning.
That's a good point. It's a reminder that AI development is still a very human-driven process.
It is. And that human element is crucial to ensuring that AI is used ethically and responsibly.
Well said. So we've talked about the limitations of TTT, but let's get back to the exciting stuff. You mentioned that pre-training on massive data sets actually hurt performance on ARC.
Yeah, that was a surprising finding.
Definitely not what you'd expect. You'd think more data would always lead to better results.
Right. But this suggests that the type of data matters more than the amount.
So it's not just about feeding the AI a fire hose of information.
Nope. It's about giving it the right information at the right time.
Information that's relevant to the task at hand and that helps it develop the specific skills it needs.
Exactly. And this finding really highlights the need for better methods of generating synthetic training data.
So we need to get smarter about how we create the data that we use to train AI.
We do. We need data that's more diverse, more representative of the complexity of the real world.
And that can help AI systems learn more effectively.
Right. And this is where collaboration across different fields becomes really important.
Like we need computer scientists working with psychologists, linguists, cognitive scientists.
Exactly. We need people who understand how humans learn to help us build AI that learns more like we do.
It's about bringing together different perspectives to create AI that's not just powerful, but also aligned with human values.
Well said. And this brings us back to one of the most exciting things about TTT, its potential to bridge the gap between neural and symbolic AI.
Yes, you mentioned this earlier. Can you remind me what those terms mean? Neural AI, symbolic AI.
Sure. So traditionally, these two approaches to AI have been seen as very separate, almost like competing paradigms.
Okay, I'm intrigued. Tell me more.
So symbolic AI, as the name suggests, relies on symbols and rules.
So it's more like traditional programming, defining a set of instructions for the computer to follow.
Exactly. It's very logic-based. Neural AI, on the other hand, is inspired by the human brain.
So it's more about mimicking how our neurons work.
Right. It uses these massive networks of interconnected nodes to learn from data.
So it's more about pattern recognition and making connections.
Exactly. And both approaches have their strengths and weaknesses.
Like symbolic AI is great for tasks that require clear logic.
Right, like math or chess.
But it struggles with things that are more ambiguous, like natural language.
Yep. That's where neural AI shines. It can handle messy, real-world data much better.
But neural AI can be kind of a black box sometimes. We don't always understand how it's making its decisions.
That's true. And that's where TTT comes in. It could make neural networks more transparent, more compatible with symbolic AI.
So it could be the key to combining the best of both worlds.
Exactly. Imagine an AI system that has the intuitive learning power of neural networks, but also the logical reasoning of symbolic AI.
That would be incredible.
It would open up a whole new world of possibilities.
Like AI that can not only solve complex problems, but also explain its reasoning in a way we can understand.
Exactly. It could revolutionize fields like medicine, education, finance, you name it.
This is getting me really excited about the future of AI.
Me too. And remember, this research on TTT is just the beginning. There's so much more to explore.
I can't wait to see what they come up with next.
It's an exciting time to be following this field. Who knows what breakthroughs are just around the corner?
All right, so let's get back to those ARC puzzles, the ones that really test AI's reasoning abilities.
Yeah, they're pretty unique.
You said they're not just about finding the right answer, but about understanding the logic behind it.
Right. Like it's not enough to just memorize a solution. You got to figure out the underlying rule, the principle that's at work.
Okay, so remind me what these puzzles actually look like. What are we dealing with here?
So picture a grid, kind of like a chessboard, but simpler.
Okay.
And instead of black and white squares, you've got these colorful shapes and patterns arranged on the grid.
Gotcha.
And each puzzle gives you a few examples. You see a starting grid and then a transformed version of that grid.
So it's like, here's the before picture, now here's the after picture.
Exactly. And you have to figure out what happened in between, what rule was applied to transform the first grid into the second one.
Oh, I see. So it's like a logic puzzle, but with visuals.
Exactly. But there's a twist. You only get a few of these examples to work with.
Oh, so it's not like you have a ton of data to go off of.
Nope. The AI has to figure out the rule based on very limited information.
That sounds tough.
It is. And then the real test comes when they're given a brand new input grid and have to predict what the output will be.
So they have to apply the rule they've learned to a completely new situation.
Precisely. And that's what makes these puzzles so challenging for AI systems.
It's not just about memorizing specific answers.
Yeah.
It's about understanding the underlying concept, the abstract relationship between the input and output.
Right. It requires a level of generalization that a lot of AI systems struggle with.
No wonder ARC has been such a hurdle for traditional AI approaches.
Yeah, it really highlights the limitations of those methods that rely heavily on pre-programmed rules or massive amounts of pre-training data.
Because these puzzles require a different kind of intelligence, a more adaptive and flexible way of thinking.
Exactly. And that's where test time training comes in. It gives AI the ability to learn and adapt on the fly to figure things out in real time.
So it's like TTT is giving them the tools to think more like humans?
That's a great way to put it. And the amazing thing is it actually worked. The researchers found that TTT led to significant improvements in performance on ARC.
So the AI was actually able to solve these puzzles better thanks to TTT.
Much better. In some cases, the TTT-trained model even reached a level comparable to the average human.
Wow, that's impressive.
It really is, especially considering how challenging these puzzles are even for us.
So it's not just about making AI better at puzzles, it's about fundamentally changing how we think about AI and its potential.
Right. Maybe instead of trying to cram all the knowledge into AI beforehand, we need to focus more on giving it the ability to learn and adapt on its own.
To be more like curious explorers than just rule followers.
Exactly. And TTT seems to be a key to unlocking that kind of dynamic learning in AI.
And if it can do that with something as complex as ARC, just imagine what else it could be capable of.
The possibilities are pretty mind-blowing when you think about it.
This has been an incredible journey into the world of test time training.
I agree. And it's just the beginning.
Exactly. We're just scratching the surface of what TTT can do and the implications it has for the future of AI.
It's an exciting time to be following this field, that's for sure.
Well, thanks for joining us on this deep dive into test time training. We've covered a lot of ground, from the challenges of abstract reasoning to the potential of TTT to revolutionize how we build and interact with AI.
It's been a pleasure exploring these ideas with you.
And to our listeners, thanks for tuning in. We hope this has sparked your curiosity about the future of AI and the incredible things we might be able to achieve with it. Till next time, keep exploring, keep learning, and keep pushing the boundaries of what's possible.